It's going to be some kind of a force. So this gives me force times distance is equal to time times current times voltage. Can you see anything here that's interesting? Time times current times voltage. What is current? Amps. And it's a fundamental unit here. I don't know why. I don't know why they chose to do that. Maybe it's historical reasons. But tell me what an ampere is, physically. Charge per second. Charge is the dimension. What's the unit? Coulomb per second. That's right. Now, they made Coulomb a derived unit here, electric charge. And what is it? Seconds times amps. I think that's backwards. Because a Coulomb is a certain number of electrons, so you can express it in moles, 90 by Faraday's number, and then you could make current a derived unit. But that makes more sense to me, but it's not how they did it. That's not important. The important thing is that I could take this, based on what you said, what is time times current? In dimensions? Charge. Yes. So now, I don't know if you remember from physics, but there's two formulas that we've found when we broke down the units. When we analyzed the dimensions, we found two fundamental formulas from physics. I'm going to use abbreviations now. I'm not using this for watts. I'm using that for work. Work equals force times distance. Do you remember that? Or maybe you might have seen it, F, the integral of f dx. Same thing, it's just you're doing this a bajillion times over very infinitesimal distances. And this is you can do if you have a constant force over some distance. Now, there's another expression for work in an electrical system. Do you remember what it is? Work equals, W equals QV. You don't remember that? Little q, big V, that's the way I usually saw it. Charge times voltage. So that's all we've done. Now, if you remember this, you don't have to go through all of this. But the point is that if you forget, all you have to do is look at what the units mean and you'll be able to get it back. And if you understand how this fits together, it makes it easier to remember, actually. So this is how we're going to get a force. We've already got a voltage and a distance. We just need to figure out how to get the charge. So how do we get a charge from what we're given here? Let me turn the screen back on. One thing I can do when I start erasing here, in case it doesn't show up on the video, I'll just so how are we going to get a charge out of that? Because if we get a charge, we've got the voltage and the distance, then we should be able to get a force. Okay, so Now, this is a different way of doing the problem. The other way you've done the problem, to think through what the physics means, is also a valid and important thing to understand. But if you do this in parallel, it'll really strengthen, I think, your understanding. So, how do we get a charge out of this? Number 2, we've got 42 grams of sodium chloride. How do we get a charge from that? They want the force in pounds on what? What do they want?
Positive.
On the positive charge. So where's the positive charge come from?
Sodium.
Sodium. So what's the charge in coulombs? If we get it in coulombs, then we've got volts, and we've got angstroms. We can change that to meters. Now we got all the same system of units, and we should get an answer in newtons. So how do I calculate a charge from 42 grams of table salts? First semester chemistry, a long time ago, huh?
You just have to.
Say it again, louder.
Convert to moles.
Convert to moles. Good. Let me see something here. Guess a fundamental dimension. Good. All right. Go back. All right. So how do I do that? 42 grams in moles. You could consult the periodic table, or you could allow your eye to wander up the page to the question number 1. Just happen to go up that far. You don't have to go to the periodic table if you notice that. So how many moles do we have in 42 grams?
42 over 58.5.
That's right. Because if I say a mole of salt, I'm going to erase some here so I can write some more. I wonder if I can flip it over. Not sure that's going to work. All right. Let's keep that there. That. Force. Charge. Times voltage. Over distance. So that's energy, work, joules, meters. And that should get us a Newton. So, 70 times 10 to the minus 10 meters. Okay, so 42 grams NaCl. And I learned this in high school chemistry, and I think it's a very good way of doing it, just to make sure. Draw this little thingy. Horizontal line and a vertical line. And then here we have 1 mole. We want 1 mole. We want moles. And that's 58.5 grams for NaCl. We draw another line there. So we can cancel this, cancel that. That will give us moles. That's the units left. So it's like you said, 42 divided by 58.5. But we don't have to stop there because we don't want moles of sodium ions. We could have said, okay, this is moles of sodium and chloride, but there'll be 1 mole of each. So I can call that a mole of sodium ion. and it will be the same. As the, it could be the same as the chloride. Now, because it's fully dissociated, that means that every bit of NaCl, there's no one sodium ion, one chloride ion. Now, I want coulombs. So how do I get from here to coulombs?
Faraday?
And what is Faraday's number?
96,000.
Yeah, it's the last page of chapter 3. There's a little list of constants there. I want to put a little sticky note on that page. What is it?
96,487.
96487 units, please.
Coulomb per gram.
Coulombs per gram. Really?
It says absolute coulombs per gram equivalent.
Coulombs per gram equivalent. What's a gram equivalent?
That's a mole. It's
Yeah.
looking at moles.
Yeah, look at them being tricky.
That's what, that tripped me up too when I saw that.
Yeah, actually, the first time I saw it, it made me.
And then I
do
like
the same.
saw the answer and it was,
So this will give me a charge in coulombs. If I then multiply that charge times the voltage, .3 volts. Now, notice something. We had a formula over here, work, and we'll put here in joules. We'll just say we're going to do it in joules. Is equal to Q, charge, coulombs, times the V, in volts. That means a volt must be equal one joule per coulomb. That's another way I can express volt. And if you broke it down into those fundamental units, where's volt? There it is. That's got to come out to a joule per coulomb. If you take a joule and divide it by a coulomb, it's got to give you this, or the laws of physics are incoherent. So this is going to be a joule per coulomb, so it's going to make volts. This is going to be joules. So we can say here joule per coulomb. And we know that is going to cancel that. Okay, we got the moles canceling. And then we have a distance. And this is going to be a Newton meter. It's joule. And then we have this distance, which is 70 times 10 to the minus 10 meters. And that is going to cancel that. So that should give us an answer in newtons when we multiply all these out. And you can see when you do this thing, and by the way, if I see you doing this and I can follow it very clearly, very good chance you're going to get full credit, or at least, even if you made one numeric error, I'm going to give you majority of the credit for thinking through and showing me that you're following the units and the way they cancel to get the answer. So multiply all that, and what do we get? Somebody tell me.
times 10 to the 12th.
2.97 times 10 to the 12th newtons. Are we done?
90 pounds. Force in pounds.
Good. And so the convention, we have 2.97 times 10 to the 12th newtons.
Just
And what's our conversion factor?
multiply by 0.2248 pounds.
Why did they say pounds force?
Pounds force, yes.
Why did they say pounds force? Why did they say that?
Because it's not a weight, it's a force.
A force and a weight. A force is a weight. It's not a mass. Sometimes they use a pound. It's very strange. And British imperial units are strange. So anyway, that gives us the answer requested to the problem, which is 6.67 times 10 to the 11th pounds.